Hello everyone, my name is Li Songfan. I'm a PhD student in UESTC. Today, I'm happy to share with you our recent work on Internet of Things. IoT has become a part of life. Sensors give us a reliable way to sense a physical condition. Then, wireless communication makes end devices easy to upload their sensor results to Internet. In the current design of end devices, a microcontroller has to be employed as a master to operate various sensors and deal with the wireless communication. However, the use of microcontrollers introduced two intractable problems. First is high power consumption. Recently, backscatter has significantly reduced the power of radios down to only microwatts, but many of the MCUs still consume milliwatts power, so MCU becomes a major bottleneck for energy optimization. Second, the end devices needs for reconfiguration across different sensors. If we change the sensors, we have to rewrite the embedded code, change the hardware connection, and even make a new PCB, which makes the reconfiguration so difficult. In this work, we take the first step to ask a bold question. Can we take a microcontroller away from the design of end devices? If we can do this, we can reduce a major power consumption from the current design and eliminate the need for embedded programming for much easier reconfiguration. We envision the Internet of Microchip architecture. The control of sensors is offloaded to a gateway, and the gateway has direct access to the sensor chip via wireless communication. This architecture brings some interesting features to the end devices, including ultra-low power due to the elimination of MCU, and is easy to reconfiguration because of no need for embedded programming. In addition, many sensor chips have the standard interface to be accessed, for example SPI and I2C. This architecture allows the standard sensors plug and play on end devices because they have the same interface. Our key challenge lies in the fact that the traditional design, the MCU is deployed to receive baseband signal from the radio and operate sensors through standard bus. Without MCUs, how to leverage the radio to directly talk to the sensors? We address the challenge and build the first proof of concept for Internet of Microchips. On the downlink, the gateway directly controls the SPI sensor using R2B communication. We highlight the concept of R2B as a novel communication paradigm that allows direct data exchange between radio and bus. On the uplink, the end devices convey sensor results using SPI backscatter to save the power. First, let's see the R2B communication on the downlink. The problem of achieving R2B is the total different communication types between baseband and the SPI bus. The SPI requires data and clock two signals for data receiving. To convey SPI symbols on the downlink, we leverage PIE format to stitch data and clock information. But the PIE and SPI have different symbol definition and synchronization scheme. For example, PIE needs one wire to transmit data, but the SPI needs two. To overcome this problem, we design a PIE to SPI demodulator to directly convert the PIE symbol to the SPI symbol. The PIE symbol first is input into a voltage integrator, and we can discriminate the PIE data according to the pin voltage by a threshold. On the other branch, the PIE signal is also converted to a clock signal through an inverter gate. The clock is used for further SPI bus communication. Then the discriminated data will be adapted to transmission on the SPI bus to the sensor. You can see that the PIE baseband signal is directly converted to SPI signals by a simple analog circuit. Now we have covered the first aspect. Let's go on to the second. How does the SPI sensor send data to the gateway? To achieve SPI backscatter, we have to solve two problems. First, the output of sensor data should be driven by a reference clock provided by the MCU. Without MCUs, how to generate SPI data output? Second, assume that sensor has already generated the data and conveys using backscatter, but the receiver lacks the SPI clock information and cannot receive the correct data. Our basic idea is to leverage an external clock from the gateway. The gateway performs a downlink PIE transmission to deliver data and clock to sensors, and the clock is also used to generate output data, so the first problem is solved. Then the output data will operate the backscatter switch to reflect the PIE signal. Given that the PIE contains the clock information, the receiver can successfully decode the uplink data. The first demo we show is a programming-free wristband. It includes an accelerometer that is controlled directly by the USRP through R2B communication. I'm going to show you the demo video. You can see that the USRP displays the XYZ information from the wristband. The cool thing here is that we don't need to write input code into the wristband. The second demo is a plug-and-play interface as an extension of our prototype. We built this interface to allow SPI chip plug and play. The following video will show you how it works. We want to add a humidity sensor to a prototype. First, we plug a sensor into the interface. Then, we load the prepared script of the humidity sensor at the USRP. The USRP will automatically interface with sensors and read the data back. We envision that with that architecture, billions of sensor chips can be directly connected to the internet, and the design of IoT-empty devices can be minimized. The keywords of those devices will be ultra-low power, programming free, and plug and play. Thank you for your attention. Please see our paper for more information.